Okay, so in 7.3 we're going to be talking about the best fit line and prediction. Another word for best fit line that you may hear more common is regression line. And this allows us to take the correlations that we've found and create a line that we can draw through our points to say this is what the trend looks like. That's another form of it. And in Excel, that's what they call it, as a trend line. And use that information to calculate what values, predicted values of what they should be. So as long as you are within that range, you can make predictions. Given a few other things which we're going to talk about, but that's the main thing that we're going to be looking at here is this best fit line. So the best fit line, or regression line, or sometimes they call it the least squares regression line, is a line on a data on a scatter plot where the points lie closest. The points that are all on their line closest to that line than any other line. Because we could draw an infinite number of lines here. I could have a line going this way or this way. I could have it up here. I could have it down here. But this particular line right here, those points are statistically closer than any other line. And to calculate how statistically close, they actually call this thing called the least squares. And what they do is they find how far each point is from the line, and they square the distances. They add them all up. They come up with a number. That sum of the squares is, for this particular line, is smaller than any other line that we could create. That's how we know it's the best line. So, thus the least squares regression line is a common term that you might hear. So once we've created that line, and I'll show you how to create that line in a minute, we use it to make predictions. Okay, but there's some rules. Okay, if there's not a high correlation or strong correlation, positive or negative, doesn't matter, whether it's positive or negative, as long as there's not a strong correlation, that means close to 1 or negative 1, then our best fit line isn't going to be very good at creating predictions because we have points all over the place. So the closer the regression is to the correlation is to 0, the worse it is for predicting. Don't predict outside of the data. So if all of your numbers are between 0 and 100, don't think of what's going to happen if I put a 500 in there. It doesn't make any sense. We're outside of that area. While we might make a prediction, and we often do, it may not be reliable because things may change after the data points that we're looking at. So that's why we don't want to make predictions outside of that. Best fit line is on past data. May not be valid for future or present data. Things may have changed. We may be looking, let's talk about polio rates. And, they have something that they looked at, let's say the age of the mother and polio rates. Well, that's changed now because polio has pretty much been eliminated. So the age of the mother and polio rates wouldn't really make sense to predict anymore. Okay. Also, parents are, the average mother age is much higher than it was in the past. So those two things don't make a lot of sense. We're looking at different populations. We're taking information from one country and basing it on another. So we might look at, well, they're going to give us some examples, but we might look at China and birth rates and pollution and compare that to a Scandinavian country, or vice versa, and say, well, we did a lot of these studies in China, and we looked at the birth rates, and now we're going to look and see how it affects, Scandinavia. Well, Scandinavia is a completely different area. They're already a modernized country. You might take the idea looking at China and then look at, third world countries in Africa that are developing, because those are starting to become similar to China. But you can't take populations that don't make sense with each other. They may not work. If there's no significant correlation, because it's not a linear relationship, our best fit line is a straight line. it won't make any sense. So if we have the subgroups that we talked about, or we have something that is nonlinear, well, when we do our regressions from those correlations, they're not going to make any sense because we're trying to draw a straight line for those. So those are our ways that we have to be careful when we're using our best fit lines to make predictions. So now here are some examples. You found a best fit line for correlation between number of hours people exercise and the number of calories they consume, which we did looked at last chapter. And you've used this correlation to predict that a person who exercises 18 hours a day would consume 15,000 calories. Well, our data only went up to a certain amount of time. 18 hours is way out. There's no possible way to exercise 18 hours a day and then eat 15,000 calories, because you only have 6 hours left in the day and you have to sleep at some point. So that doesn't make a lot of sense because we're way outside of our boundaries. The second one says there's a weak correlation between essay scores and college grades, and it's true. Can we use this to predict college grades based on SAT scores? Well, while we can, because there's a weak correlation, we shouldn't do it. Because weak correlations tell us that there's not going to be a very good predictor. So this is also a reason to not do this. We have historical data showing negative correlation between birth rates and affluence. So the greater the affluence, the lower the birth rates. Would this be useful today? And possibly, but possibly not, because it's old historical data. They're looking at current birth rates. Should we predict high birth rates in Russia because it's a poor country? And well, the data is not correct. It's old, so it may not. Things may have changed. I mean, it very well may be correct, but that doesn't necessarily guarantee that it's going to be, because it is old historical data and we're trying to put it into present time. D, here we have a China, and we're looking at correlations that are useful for museum exhibits that Chinese children enjoy. So would that make sense for an Atlanta school museum? And because we're looking from an outside source, not necessarily our culture, doesn't make a lot of sense to use this as a predictor, because Chinese children are different from American children, and children in New York are different from children in Atlanta. They may not be a good predictor. So we shouldn't use this data to predict something in the United States. Scientific studies have shown a very strong correlation between children's ingesting of lead and mental retardation. So paints containing lead were banned. Well, this makes sense. Okay, the studies were there. We're looking at children. So the populations are the same. There was a strong correlation. Makes sense to use this as a predictor. The last one, a large data set. You've made a scatter diagram of salsa consumption and education. And you've decided that people who eat a pint of salsa have at least 13 years of education. Well, those two things have no relationship. So it makes no sense to compare them. And so therefore making predictions off of how much education you have to how much salsa you eat doesn't make a lot of sense, because there's no relationship between those two things. There may be coincidental relationship, but there's no real relationship between them. So you don't use it as a predictor. And those are things just to keep in mind when you've done correlation with your data. Should I make a best fit line? And will it make sense to use that as a prediction tool? I thought I got rid of these. So correlation coefficient. Now, we take our correlation coefficient, which was R, and we square it to get R squared. This value here tells us the proportion of the variation in the dependent variable based upon the independent variable. So basically, what percentage of y is explained by x? And if I look at the next slide here, if I have a correlation coefficient of 0.9 or a negative 0.9, that says that x basically explains 81% of the variation in y. So yes, we're going to be off, but most of it is explained by y. Whereas notice as we go down in correlation, to 0.5, let's say, if an r is 0.5 or negative 0.5, our explanation, the percent of variation, is only 0.25, or only 25% of the variation in y is explained by x. So, and you can see that when we get to 0.2, there's almost no explanation in the variance. So that's why low correlations can't be used as predictors, because r squared, or the amount of explanation of y by that value of x, is negligible. If a correlation is 0.2, the r squared becomes 0.04, or 4% explanation. So we can see that that's not a very useful tool for predicting. And so we always calculate our r squared to see, is this going to be a useful thing to explain variation, and we can see how much of it will be done. Now the next part here is finding best fit lines. And like I said, you can draw as many lines as you want, and it's very hard to do. So you're not going to actually do that. You're going to actually have something calculate the formula for you and then draw the line on the graph. But what we do is they say draw any line and measure the vertical distance between each data and the line. Then we square it, because you're going to have positives and negatives, and so we don't want to add them up together, and we'll get 0. So we find the vertical distances, or residuals is another term for that, and we add those all we square them and add them all together. And so if you get a large sum, okay, that means it may not be the best fit line. We keep looking and drawing our line and drawing our line and drawing our line until we get the smallest value that we can, the least squared value. Okay, so that best fit line is the one that minimizes the sum of the squares, or has the least sum of squares, least squares line, regression line. So it has the smallest amount of vertical distance, or smallest amount of residuals for all of those lines. That's how it's created. That's how we don't do it that way anymore. So what we do now is we have formulas to help us build this. So remember from algebra, you had y equals mx plus b, where m was the slope and b was the y-intercept. Well, same thing is going to happen here. We're going to create a line where we have m as the slope and b as the y-intercept. And now, remember when we found m, we found the change in y over the change in x? Well, we can't quite do that because we have all these points, and we have hundreds of points to look at, or thousands of points to look at, or 6 points to look at. And so we can't just calculate that because none of the points are on a straight line. So what we do is we take our standard deviations. Notice here we have our standard deviation of y divided by the standard deviation of x, and then multiply it by the correlation coefficient, r. When we do that, we get our slope. Then we can find our y-intercept. And now remember, to find y-intercept, you can take the slope and a point on the line. Well, the mean of both values, the mean of x and mean of y, will be on that line. So you take the means of the x and the means of the y, and you plug it into this formula. So you take the mean of y and the mean of x, plug it in, plug in your m, and so you multiply your slope times the mean of x, subtract that from the mean of y. That will give you your y-intercept. Okay, because notice when we have y equals mx plus b, well, to get b alone, we subtract off mx, which is what they did here. So we do that, we can get our y-intercept, and we can type that in, y equals mx plus b. But if you use your calculator or Excel or a statistical program, it usually comes out as y equals b0, which is the y-intercept, plus b1, which is the slope, times x. So you may see this formula here, and so you just have to remember that, oh, this is not the slope and this is not the y-intercept. This is the b0 is the y-intercept and b1 is the slope. So I'm going to show you how to do this in Excel in a few seconds. I just have to get an Excel sheet up. But that's the end of the notes here through 7.3. Oh, I guess it isn't. Sorry. There's one other thing here, multiple regression, which says that we may have more than one thing calculating that we can use to calculate best fit. So because there's not always just one thing that determines weight. There may be height, there may be gender, there could be calories, caloric intake. We use all those things to calculate how much you should weigh. So because there's lots of things that allow you to get an answer, to determine that are dependent variables that create one thing, we can actually do a multiple regression. And they say multiple regression allows calculations of a best fit line when you have one variable, which is dependent, and a combination of more than one variable, which is independent. So here they're talking about the diamonds, so price versus weight and color. And in this case, they give you a big R squared. So capital R squared just tells you the proportion explained by more than one value. And we can break it up and find each value and see how much each one contributes to the overall. But so what they do is they kept this big R squared, which says that we've done multiple regression. And this is how much is explained by all these variables that we have. And that's the end. Sorry. Okay.